Thank you so much. So welcome everybody to the Coastal Resilience webinar talks. This is a webinar that we try to held every month, and we explore case studies, research stories of resilient coastal communities or aiming at become resilient coastal community. And we also show some real-world solutions that can inspire you. Each session features leading researchers, educators, and practitioners. We are a center that works within the United Nations Decade of Ocean Science, 2021-2030, where we have decade challenges and decade outcomes that we are trying to reach by the end of the decade. You recognize community resilience to ocean and coastal risks as one of our challenges, and as an output, a safe ocean. But many of the challenges contribute to coastal resilience. And so we try to interface different communities that work on the specific challenges. So the Decade Collaborative Center works within a partner alliance network that has CMCC as one of the main partners, also co-organizing these webinars, and Deltares that also helps, and soon we will be joined by Heron from Germany. Deltares is from the Netherlands, and hopefully more to come before the end of the decade. So please connect with us through our channels. You find the QR codes here. You can see where we are. So today it is my extreme pleasure to have a talk on learning principles for youngsters, and the speaker we are honored to have with us, Professor Sung Yong Kim, associate professor at KAIST. So KAIST is the Advanced Institute of Science and Technology in the Republic of Korea. And he received his PhD in oceanography from famous Scripps Institution of Oceanography. And then finally, he went back to Korea, and hopefully we will continue to work together in the global ocean. His research interests include coastal circulation, submesoscale processes, and operational coastal observing systems. So to conclude, apologize, sorry. So we have a Q&A session. You will not be directly posing the question to the speaker, but you have to post your question on the Q&A session. So you should find a button with written Q&A, and the audio, your audio and video will be deactivated. And so please write your questions at the end of the talk of Professor Kim. We will be having the question and answer a discussion, which we value very much, as well as the speakers. Just to let you know that this webinar will be recorded, and by participating, you consent to the recording. Thank you very much. So please, Sung Yong, the floor is yours.
All right. Thank you very much for introduction. So thank you for the invitation. I'm going to share my slide. All right. So as we will have fundamental information on the seawater properties today with ice melt experiment. This is part of the one of the experiment that I in my book that I published this year. Yeah, so let me start with this way. We're gonna pose a question with this ice melt experiment. Before that, we need to learn what the seawater properties and fluid density. And I'm gonna review what's the isometric experiment with the TS diagram, which we define in the fluid and seawater properties. Then I conclude. This CMCC webinar is more solution and they're targeted audience, but I prepared this talk for young audience. So also the teachers, and you can use this material for to educate them for ocean and also seawater properties. All right, so I'm gonna start off this isometric experiment first. So we prepare two patch of water, so fresh water and fresh water with salt. So just to make a seawater one side, so it has room temperature water. So as you notice here, green is the fresh water, the seawater or salty water, and the blue here. And we will put the ice on the both container and see if what's the outcome, which ice melt quicker. But I didn't know that I can hear some voice from the audience, but I like to. This is the kind of question that I want to pose to you. If you place on a ice with the same the room temperature fresh water, room temperature seawater, which ice melt quicker? I prepare a video clip, then I'm gonna show you what you may expect it. However, please guess before you watch this one. Maybe you can raise your hand if you think the freshwater side will be melted quicker, or you can raise your hand. The seawater side ice can be melted quicker. So I'm gonna play this one movie in a fast forward, then see if what we got. Okay. All right. So we prepare fresh water on the left and salt water. I'm sorry. On the right, and we place the ice cube, the same amount, and the salty water first, and fresh water. Then we try to visualize what happened in the two container. So we drop the dye. Let me go for fast. Yeah, we drop the dye on the top over here to see if what happened. So I just stop here. We put a dye on this side to visualize what's happening. So you might see the TA, he didn't drop that well, but it penetrated all the way. But you might see there might be significant difference of the dye patterns. So I'm gonna go further. So as time goes, you will see what happened in the left-hand side and the salty water side, right-hand side. And let me move a little bit faster. All right, a little bit faster, more. Okay. We try to drop the dye in the same amount, but it looks like you might consider, oh, the dye has contaminated all the water or those experiment, but as you notice, there might be something going on the left-hand side, but we don't see that much on the motion on the right-hand side. Let me go further, see if what you got. I'm gonna go very fast. And we just take a look at the top view, early 5 minutes. We don't see that much difference, but a little bit of the ice, a little bit bigger on the right hand side. But if you take more than 10 minutes, I'm gonna go fast forward, then move it to the end, 50 minutes. You will see the top view at the end. So what you got here is salty water side. Ice is a little bit bigger than the freshwater side. So uh, please don't be confused with this one. The concentration of dye, the dye or the saturate the top layer on the salty water side. So you, even though it look like the the dye is all the water depths, but they only stay on these top areas. So anyway, so the conclusion I got, the result, ice melt quicker on the freshwater side. We will see why. All right, so let me switch the screen. All right, to bring up those questions for more detail, I'd like to start off the freshwater properties. Sorry, the seawater properties. The seawater usually considered as salty, which contain the chlorine and sodium NaCl, which is the chlorine component, and also it has a temperature. We may say seawater has cold or warm. So those saltiness or salty and temperature or cold and warm will be the primary properties. So based on those two information, we may consider whether it's lighter or heavier than fresh water. So fresh water doesn't have any saltiness. So you may just imagine. So when you say that's lighter and heavier, we have to consider the density, which is the uh, basic information on the fluid. Density is the ratio of mass to volume. So if you have container and the fluid, if you give a mass divided by volume, we call the density. So the easy way of the density will be if you have uh, same density of fluid, if you have more uh, more volume, that means more mass. So same density, you have more mass and more volume. And also if you have same volume, more mass means the hay has a higher density. The reason that I bring up the density here, we can consider which one is heavier and lighter. So if it's high density, low density, uh, you can say the high density is more much heavier and lower density is lighter. Depending on this density, we use this fluid of density for the how they reacted the gravity. So I brought two sets of cartoon here. This is, let's say this is a water parcel, fluid parcel, has a small container, but it's different size, but same density, let's say. If it's the same density, the volume can be considered as a mass. So it's more mass on the underneath and the lighter one on the top. If you look at the right hand side, it's a more volume. That means more mass. And also, if those mass is on the Earth, it's under the gravity. So if you have mass times gravitational acceleration, which give you the weight. So you might say weight or density issue, we can determine which one is heavier and lighter. So on the left-hand side, it's a heavier one is close to the center of the Earth, and lighter one is a little bit far away from that. The right-hand side is the opposite configuration. So you might consider in nature, it tends to heavier one tend to close to the center of the Earth, which means the left-hand side was show the more stable condition compared to the right-hand side. If you go to some other mountain, or some people just put on a little bit of the rock on the in a row, but you might see a heavier one in the bottom, or bigger one in the bottom, smaller one in the top, so that make a stable condition. But if you put on in the opposite order, you might feel like, oh, it's unstable and it may fall off in the given situations. So you may consider in nature, the heavy water, or the heavy one, or higher density one, or more weight one, stay on the center of the Earth. So if you consider in the ocean, heavier one stay on the deep water, and light one on the surface. That's the natural configuration of the fluid. So I just put on a container here. This color indicates the, let's say, density. The dark red is going to be higher density compared to the light one. So stable water columns looks like this way. Heavier one stay on the below, and light one on the top. So this is a kind of very stable water columns. And let me consider this way. If you move the heavy water parcel to a little bit over here, what do you expect? What happened? So heavy one, move small parcel to move to the light place. You may see this water parcel, moving water parcel, is relatively heavier than environment. That means it may fall down. It tends to go down. Or if you move light water parcel to the underneath, it may feel like lighter than environment. That means they tend to float. So this given density, or stratified, or higher density underneath and the lighter one at the top, it's a more natural, stable condition. However, if you move that, if you place in the opposite order, the water parcel tend to going back to the original place under gravity, so which generate the flow motions, and this is related to the ice melt experiment. All right. So, okay, let's move to the how density distributed and the vertically in the oceans. Oceanographer usually we sample, physical oceanographer sample the ocean temperature and salinity. We took a boat and go out, put on a sensor in the vertical. This is the RC interface, and this is a profile present you to how they distributed in the vertical. So if you look at the temperature profile, ocean temperature typically is warm at the surface. As you get deeper, it's cold. And also the salinity, typically in the fresher or the less salt the surface, as you get deeper, it's gets saltier. The combination of those two, temperature and salinity, provides the density. Typically, density will be increased with depth. As I mentioned, in nature, it's a stable condition. So, it given water density, stay on the light one on the top, heavier one on the bottom, which is close to the center of the Earth. This temperature and salinity, their combinations determine the density, and the one, the physical oceanographer, they developed the idea how we gonna make a determine the density based on temperature and salinity. So we make a diagram which defined by the temperature and salinity. So this is the two-dimensional view of temperature on the y-axis and salinity on the x-axis, and has a range to 0 to 25 Celsius and salinity 0 to 35. And there are two combinations generate the density, and the contour that I show you here is show the density contour, so which is a constant density along this red contour. And typically it has a lower density on the top left and the high density on the top right, which we call the isodensity line. So just imagine if you have constant fresh water, zero salinity, compare the water at here and here. As you get your higher temperature, density will be lower. Also, if you have constant temperature water, higher density, I'm sorry, the higher salinity water is higher density. So along this line, along this contour, because the isodensity line has the same density, so you can make a same density of seawater as a combination of T and S. So along this line, we consider as a salinity will be the same. I'm sorry, the density will be the same. Sorry. Okay. So let's just remind you to what we had in the beginning. We prepare fresh water and salty water in the room temperature, put on ice, and see if which ice is melt quicker. And it turns out, based on the experiment that I showed you in the video clip, fresh water side has less ice. And also we put on a dye on here, and it looks like there's something going on in the vertically. But in the ice seawater part, we don't see that much vertical motion. That's why we don't see that dye activity or diffusion over here. The reason that I can say is there's circulation going on the freshwater side, and the other one doesn't have that much strong vertical motions of the fluid because it has a different configuration of density. So let's use the TS diagram from here. I placed the A, B, C, D on the seawater properties in this segment. So which is the freshwater side, room temperature, and ice melted area in the freshwater side, the B, and salty water, the C, room temperature, and D is the ice with the seawater side. So let's mark where those A, B, C, D located on the TS diagram, see if what's the density looks like. And based on the density, we can imagine which one is lighter and which one heavier, and see if whether they have unstable conditions and stable condition, then we might find the reason that we have which ice melts quicker. All right, so A is a freshwater side, room temperature. So I put on a mark here. Temperature on the y-axis and x-axis, the salt salinity here. So room temperature, let's say 20 degrees Celsius, and close to the zero, but I didn't put it in the here, but A is here, right? And if you put on the ice on the top, ice will be made by fresh water. So ice will be located here. Maybe B can be mixture of A and ice. So their density or their location it will be between A and E. So you may consider if it's a very short time, it close to the ice, but it's as time goes, it may have in between somewhere. So I just put on a mark on the B here. And if you look at the salty water side, room temperature, same temperature of the A, and there's a saltiness of a C, so I mark on the C here. And ice will be the same condition. If you look at the location of D, it may stay on the between C and ice, so I put on a mark on a D. Okay, maybe if it's same condition, B and D will be the same temperature, so I put on a same temperature on the y-axis. So based on those diagram, you may compare the density of the individual water parcel here. So as I said, this is the contour of the isodensity line, lighter on this side and heavier on that. So if you compare A and B, the contour goes to this way and that way. So A will be lighter than B, okay? And if you compare C and D, D will be lighter than C. So if it's the contour on the left-hand side, it will be lighter water. So if you look at the freshwater side, A is lighter and B is heavier. That means B tend to move down, or it's unstable condition. Heavy water on the top, light water on the bottom. So it tend to move to down, going down, and mass conservation generate the move water at the top. And if you look at the C and D, D will be lighter and C is heavier. So lighter one on the top, C is heavier. That means it's very stable condition. There's no motions in the water. So in the left-hand side, the freshwater side, there are the vertical circulations, and it leads to the heat exchange, room temperature water to the ice water. So it generate, it make a ice melt, and also on the right-hand side, there's a stable condition. You don't see that vertical circulations. That's why you have more ice get smaller on the freshwater side. So based on the TS diagram, we can conclude which one is heavier and which one is lighter, so that you can imagine what happened in the behind. And that will explain in the seawater side how ice can be ice melt experiment, the meaning of that. So, okay, so there's a vertical convection circulations, and the ice gets smaller on the freshwater side. So I showed you the movie, and if I do the rephrase in the left-hand side, the freshwater, left-hand freshwater, and right-hand side is the salty water. Due to the unstable condition on the freshwater side, vertical circulations, general heat exchange, and ice melt quicker than the right-hand side, whereas it has a stable condition for light water on top, heavy water on the bottom. So if I conclude, the seawater is characterized by the salinity and temperature. This is the unique properties, and their combinations generate the seawater density. So based on the experiment that we have, we realized the ice melt quicker in the freshwater container, because in the freshwater side, the heavy water on the top sink, and due to the mass conservation, the warm water get up, and it generates the vertical circulations and heat exchange. But the other side, on the salty water side, light water on the top, heavy water on the bottom, they have stable condition, so there's no motions in the fluid. So this is the conclusion, and just I want to show you the behind physics with the TS diagrams and with the density. So it will be good tools to educate and also to understand the seawater properties. This one is I just make a analogy for coffee. I know the Italy is very well known for the coffee, and coffee has similar properties and concentrations and temperature. So the density of the coffee is governed by those two. Maybe another properties may exist, but you can make analogy with coffee. Uh, and also, this is the one of screenshot that I had with my wife at the uh, Dead Sea. Uh, it has a very salty water, so it has a more buoyant situation. So this density also is related to the buoyancy, and it make it easier to swim or it make it easier to float. But this is another view of the stable conditions and seawater properties. If you want to look at more detail on this topic, I just published a book on a cup of coffee in the ocean. So you may refer this one, and QR code you may find the website. All right, this is all that I could prepare for today, and I will try to answer for your question on the QA. All right, I'm gonna stop. Thank you.
Thank you very much, Sung Yong. Very nice. I mean, these experiments are rather novel. Um, we do other series of experiments, but the ice cube is really a nice idea. Very
All right.
nice, very original in teaching. I will copy you next year, my course, and show at the end of the lecture that the fresh water has the ice cubes melted and not the salty one. Very
Yeah.
nice. Yeah.
Yep.
So let's see if I can ask you a question.
Yes.
Meantime, I invite the people to ask questions.
Yes.
Don't be afraid. You can ask, you know, uh, Professor Kim any kind of question about the ocean. He knows everything. Anyway, my question would be, so what is the water property that is most important in climate change? Um, in climate change, and among the one that you have told us, or
Oh.
what are the, let's say, without the most important, what are the, what is happening to the temperature and the salinity of the world ocean in a
Mm.
climate change, in our climate, and in the future?
Yeah, question is about how can we connect those water properties
Yeah,
to the climate change or climate variability? Um, One thing that I pop in my mind is the TS, the temperature and salinity, and their combination provide the density and it generates the circulation in the ocean. And uh, and also if you look at the latitude wise, there's evaporations and uh, rainfall, so it has a different density of the seawater properties. So uh, I think those seawater properties more uh, it can be two perspective. One can be active way they generate the circulations, and also it's the passive mode will be by the given waterfall, the rainfalls and evaporations. They will be modified those things. So climate change or climate variability affects the TS distribution, and those combination will be generate the circulations, and those two things going give a feedback in between. And another issue will be nowadays the circulation is speed up and will slow down. That's the one of the issue in the global scale. but this density-driven flow may be a little bit very slow motions, but it'll be good to know how they can be speed up or slow down by the different distribution of density by the temperature and salinity. So that's my view on the TS on the global climate system. I hope this can be answered for you.
Yeah, thank you. It's a very good synthetic answer. I see a hand up.
There's a hand up from Michelle. I'm just gonna see if they can speak.
Can I speak?
Right.
Can you hear me?
Yeah, you can go ahead.
Yes.
Okay, well, thank you very much. I enjoyed this a lot. It's something I have to explain to my students in my planning and management of the coastal and marine environment, this salinity, temperature, and melting glacier stuff. And I wanted to ask specifically, it's very connected to what Nadia just asked, but how this how this connects to the changes in the Atlantic ocean conveyor, uh,
Yeah.
the AMOC.
Yeah.
In
Yeah.
terms of the
Atlantic
water that's
overturning.
coming off of,
Yeah.
let's say, Greenland or,
Right.
okay.
Yeah. Okay. Let me rephrase. The AMOC, which is the Atlantic overturning circulations, it's driven by density. That means the North Atlantic has the cold water generations, and it sinks down and all the way down to the underneath, and they circulate, generate this conveyor belt to as an engine of the climate change or climate variability. So the question is about how those TS, temperature and salinity, affect the AMO. Is that fair to say?
Yeah, or how what you showed us relates to that,
Uh,
and potentially to a tipping point there.
wow. Yes, this nowadays, maybe a couple of years back, tipping point issues. Couple of folks they mentioned that. I think I just want to be more careful, but this is the kind of basic information how the AMOC can be driven by density difference. So you can use this experiment for explaining the AMOC. And as I mentioned from the Nadia's question, depending on the density gradient or density difference, maybe whether they change it AMOC or density-driven flow speed or their period, that means may affect the climate. So it'll be good to know how much the density will be modified about those TS configurations. So that's one thing I can say. And yeah, I don't have that much good answer, but this experiment give it to you more fundamental informations for the overturning circulation, how they determine by the density, and which ones do we look at to know more on the AMA. So yeah, that's what I
Thank
can
you.
answer. Yeah.
I realize there's a lot of uncertainty there.
Yeah, right. Yeah.
But there have been these, every now and then there's this article in Science or something that says, we're just like, we've passed the tipping point and things are starting to happen and stuff. And yeah, so anyway.
Like the tipping point issue, I would say there's a system, and system has capability to maintain those change, but if it's over their limits, they may change their phase on the different steps. So it'd be good to know what kind of flexibility or capability that our climate system has, and see if how it changed to the another phase. So yeah, maybe you can take a look at it in that context as well. Yeah. Yep. Thank you.
So thank you very
Thank
much.
you.
Yeah, thank you, Michelle. That was a very nice question. Sung Yong, and I cannot see the question and answers now. I lost the panel. Is there something more?
No, there are no question and answers in the question and answer sections. But if anybody does have questions, they can write it in the Q&A section or raise your hand as well.
Yeah. Yeah. Well, let me say that my feeling is that we have, sort of alluded to talk about these basic principles that Sung Yong has told us today, which, sort of trying to go for these tipping points and so on. But these are very solid concepts of the physics and thermodynamics of the ocean. So I would say that it's good to learn them first and then go to the next question. And then, it's fine to try to see if there are tipping points and this, but and because we have to be alerted if something
Right.
of that kind happen. So we had in the past many other authors that were thinking about tipping points. We haven't seen them occurring due to ice melting. A long time ago, people were already in the 80s. They were saying tipping point will be crossed and the Atlantic overturning circulation will now be activated, be as strong as even completely disappear. But I think that before we go there, we should know the changes that are occurring in our TS diagram. That's very important, very solid. It makes you and there are many changes, as Sung Yong was saying. So
Yeah.
a good way to approach the uncertainty that we have in understanding climate of the Earth.
Yes. Yes. While you're talking, Nadia, we have the question on the QA board here.
Yeah.
The question is about if we make artificial circulation, is it impact on the melting the ice in the salt water? I interpret this one as the salty water has a very stable condition, and oh, the one in the if generate artificial circulations, whether it's impact on the ice, I think so. If those circulation generate the heat exchange of the high density salty water with the ice, if it generates heat exchange, ice can be impacted by those circulations. Yeah, so, but when you say the artificial means in the vertical circulation, right? Not the horizontal circulations. So I just want to make sure if you this artificial circulation generate the heat exchange, it will impact on the ice melting in the salty water. Okay. Yep.
Yep.
Yes, but I don't know which way you generate the one. There might be other driving force on the artificial circulations, and yeah. Okay.
Maybe Sung Yong, maybe
Yeah.
it could be completely artificial. So it's like, something engineers could find to enhance the vertical circulation under the ice.
Under the ice.
I mean, if we want that, we actually
Yeah.
don't that. So we
Right.
should suppress vertical
Yes.
separation and the ice. That's much more difficult. Yeah.
Okay, I have a couple subsequent questions on the what kind of dye. I think there's a regular dye on the ink. We call the ink or dye for I don't know what kind of
I use,
dye.
if I might say, Sung Yong, I use food dye.
Who's dye? Oh,
Yeah.
yes.
So
Bi
it is important.
biologically degradable dye. Yes.
Yeah. In Italy, we make a lot of colorful cakes.
Oh, that's right. Yes. Yes.
And
Yes.
so I use that dye that I use
Right.
cakes.
That's
So,
right. Yes.
and it works very well, I can tell you.
Yes.
Very well.
Great.
Food
Okay.
coloring. Yeah, Michelle. Yeah, Michelle. Yeah. Food coloring. Perfect. Yeah.
Yes.
Yeah.
I noticed there's a lady has a website on the kitchen oceanography, and she used the kitchen as the tool of the explain the oceanography, and maybe she might use the food dye or just these things anyway.
Yeah. Yeah. That's a very good input. Or we should invite her next. The food, the kitchen to learn about the ocean. That's
Right.
fantastic. Yeah. Okay. I don't know. Do you see more questions now? Okay. So maybe we can thank Sung Yong Kim
Right.
for preparing this very nice lecture and then also doing this first book, I guess, on
Yes.
we're waiting for the next one, Sung
Oh
Yong,
man.
the next one. Nice book. And one thing I want to make a comment about regaining this experimental view of the ocean. The ocean is difficult to measure,
Right.
but you can start with laboratory experiments that
Right.
you show. And this is very important especially for young children. I'm talking about elementary school. They are really attracted by, especially by food coloring. Very nice. They love the food color, but is a very, very nice way. And I have to say that I teach all the way to university with lab experiments, but also after a while you need to go at sea and really try to measure and how difficult it is to measure. And so, but this is very important that we think about experiments that show the evidence of the laws, thermodynamics, physics, and even biology and marine biology. And yeah. So thank you so much again.
Right.
Very
Yep.
inspiring. We'll see you
Right.
soon.
Yes. All right. Thank you very much, and hope this helped you to the CMCC and other educators. Okay.
Thank you, Sung Yang. Have a
All
great
right.
day, everybody.
Bye-bye.
You.
Yeah.
Bye-bye.
Bye-bye.
Bye.
Bye.